Alright, today we're going to talk about sex-linked traits, and we're going to answer the question, why are males more likely to be colorblind? Alright, so the first question we got to answer, what is a sex-linked trait? These are genes that are on the X or the Y chromosomes. Now, for our purposes, there's very few things that are actually on the Y chromosome, so we're only really going to be talking about ones that are on the X chromosome. Alright. So let's look at a female here. She's got two X's, and so this is going to be a sex-linked trait because the gene is on the X chromosome. Now, if she's got a recessive allele, she's not necessarily going to have that recessive phenotype because she could also have a dominant. The only way that she's going to have the recessive phenotype is if she has two recessive alleles, just like we've been talking about with everything else, because remember, she's got two X's, just like she has two of every other chromosome. However, let's look at a male. Males do not have two X's. They only have one X chromosome and a Y chromosome, and that Y chromosome does not have the same genes. So in this case, since that male only has one X chromosome, whatever allele is on that X is going to be his phenotype. So he only needs one recessive to actually have the trait. And this is why males are more likely to get these recessive traits. They only have to inherit one recessive to get that trait. Now, where do these recessives come from? Well, remember, the dad is actually going to give either an X or a Y. If he gives a Y, it makes it a son. If he gives it an X, then that's a daughter, because the mom is only going to give an X. So in the case of offspring, the dad is going to actually be the one that determines the sex. Whichever one he gives is going to make it a male or a female. If it's a male, the mom's going to be the one that actually determines the traits, because the mom is the one that gives a male the X. So keep that in mind. Alright, so let's look at some of these sex-linked recessive diseases. We'll really only be talking about the recessive ones because they have some pretty significant issues associated with them. First one we're going to talk about is hemophilia. And a person that has hemophilia is also called hemophiliac. And hemophilia is where the blood does not clot correctly, and people can actually bleed out from a small cut or wound. Muscular dystrophy, there's multiple types. We're going to be talking about a specific one that's sex-linked. And this is where your muscles actually atrophy or kind of go away. And most people with muscular dystrophy die very early on in life. And the final one, and the one it's not really that big of a deal, is color blindness. And if you are looking at that circle and you do not see a number inside of it, you have red-green color blindness, and you're probably a male, because it's much more likely, remember, in males than in females because they only have that one X. Alright, so remember, XY is male, XX is female. Now, in order to write these, we're going to show the X's and the Y's, and then we're actually going to put the allele above the X. So this would be a dominant, and this would be a recessive. Same way we did it with the regular dominant and recessive. Alright, so in this case, this individual will be a male, because they got the Y, and they would have the dominant trait because they have the uppercase H. This would be a male with the recessive. And notice I didn't use the words homozygous or heterozygous because they only have one X, so it doesn't really make a difference. I'm just going to say they have it or they don't. Now with females, since they have two X's, they're going to have two alleles, so I'm going to use those terms. I'm going to say this individual is homozygous dominant. So if I look at this without the X's, it looks exactly the same as our regular dominant and recessive. Two big H's, homozygous dominant. This female would be homozygous recessive, so she would have the trait. And this female would be heterozygous. And we're going to use a special term for females who are heterozygous. We're going to call them carriers. because she is carrying the recessive trait, but she herself does not actually have it because she also has a dominant. All right, so again, hemophilia, sex-linked recessive trait. Let's say we have a female who's heterozygous and a male who's normal. We're going to set these Punnett squares up the exact same way we did before. Nothing changes just because we throw these X's in there. And these would be my possible offspring. Now notice, 50% female, 50% male. It's always going to be this way. I recommend going through, putting the X's and Y's in first, then go through and put in the alleles. All right, now as far as the genotypes that we have and phenotypes, we have one male who has the recessive, and so he is a hemophiliac. We have one male and one female who are completely unaffected, and both the mother and one of the daughters are carriers. So again, Punnett squares work the exact same way. We've just got some X's and some Y's in there. All right, so let's look at color blindness. And let's look at kind of how this works as far as creating different offspring. So I'm going to use a color to indicate the different alleles. So I'm going to say blue is normal, red is colorblind, and half and half is a carrier. So let's say I have two normal parents. That would be their genotype. All their offspring are going to be normal because there's no recessives in there at all. Let's say I have a colorblind male and a normal homozygous dominant female. The male is going to give Y's or going to give X's, and since his X's have that recessive trait on them, he's going to give a recessive. The woman's only going to give dominants and X's. So all of the males are going to be fine, because remember, the woman is the one that gives the X to the sons, and all the daughters are going to be carriers. If we have a normal male and a carrier female, this is what the parents are going to give. So we're going to have normal male, affected male, because remember, the woman determines this the genotype of the male, normal, and carrier. Now, let's say that we somehow get a colorblind female, and we have a normal male. Well, since the female is going to only give those recessive X's, all of her sons are going to be colorblind, and all of her daughters are going to be carriers. Now, let's say that we have a colorblind male and a carrier female. Notice, for the first time, we have recessives on both sides. Both parents have one. So that is going to allow us to actually end up with a colorblind female. So if you ever see a female who's colorblind, you automatically know that her dad was colorblind and her mom was at least a carrier. And finally, if they're both colorblind, everybody in the family is going to be colorblind. So, to sum this all up, some key points. Remember, sex-linked means they're genes on the X or Y chromosome. We're really only going to be dealing with the X, and we write them the exact same way. If it's dominant with a big H, recessive with a little, just above the X. Males are more likely to get a recessive trait, and that's because they only have one X chromosome. Otherwise, everything works the exact same way.